Hey guys, so in this video I'm going to go over the Euler equation in a model of consumption again. And before I get into that, we're going to list out our assumptions of the model just so we can get a bit of context and so we can know the exact way in which we're going to get to our Euler equation in this under this specific set of circumstances. So I've done a previous video where I derived the Euler equation in a two-period model of consumption, and the assumptions in that model were very similar to the assumptions listed here. However, there's going to be one key difference in this case, and that is that instead of having two periods in the model, we're going to have infinite many periods, or an infinite horizon here, which means we're going to have period t, period 1, 2, 3 up to infinity. They're infinite periods basically. We're still going to have a single good in each period that the consumer aims to consumption, called CT, and earnings are going to be taken as given, which we're going to denote as Y, indexed by period T, and our consumers are also going to be given some assets at the beginning of the first period. They're going to be endowed with assets denoted AT, and they're going to get these in period T, so the very first period, and no other period after that. So they're just going to be endowed with assets AT in the beginning, and this is not going to change after period 1, 2, 3, and 4. This is going to go away. So that's an also important point to note, is that this will only occur at the beginning, and you will see in the equations that we derive after this that this will not change over time. So that's just one thing to keep in mind to avoid any confusion in the future. So in this model, what is the point of our consumers? As in, what is their goal? What do they want to do? Well, being that they consume consumption in every period, and that is the only good that they consume, this is what they get utility from. And thus, every consumer logically wants to maximize their own utility to get as much benefit from that, because they get benefit from consuming. They get utility from consuming. So they want to maximize that utility, and that's what their goal is to maximize this function. This is the utility function, and this is our consumption here. This beta is our discount factor, because, yet again, in the previous video I did on the deriving the Euler equation, which I will put a link in the description, because we're looking at consumption in the future periods, because again, we are not just looking at today's period, we're looking at all the periods in the future. We have to discount it because it's in the future. We have to get the present value and discount it, and that's what beta is. It's a discount factor. And because we're looking over infinite periods now, not just period t, we're looking at period t plus 1, plus 2, plus 3, all the way up to infinity. S is just our kind of state, our indexer to take t from t. The view S is just S is going to be equal to 1 all the way up to infinity. It's quite messy, infinite, but that's infinity. That's what S is going to be. And as I said, because we're looking at an infinite horizon, we're going to sum the consumption in every period from S equals 0, where we will just be in the first period, t, all the way up to 1, 2, 3, all the way up to infinity. And again, this is to the power of S because we have to take into account the discount factor in every period. As we get further on to further periods, S is going to increase, and the discount factor is also going to take into account that exact period that we're in the future. So that's all that the consumers want. They want to maximize this function here over our infinite periods. This is their goal. So now we're going to look at the budget constraint that is going to be faced by these consumers, because obviously they can't consume an infinite amount of the consumption good. There is a limit to how much they can consume, and in the assumptions, that limit is dictated by the income that they take as given in every period, YT, and the assets that they get given at the beginning of period 1. So one way we can start to look at the budget constraint is just simply because there's only two sources of income, is just to say that consumption in period T is equal to the assets that they get endowed with plus the income yt that they take as given, because these are the only two kind of sources of revenue, you could say, for our consumer. So this is what their consumption is limited to, is how much they get from these two things. But in the case of an infinite horizon, obviously our budget constraint can't just be this. We have to kind of tweak it a little bit to suit the infinite periods that our consumer is going to be kind of, living across. So the first thing we have to do is sum consumption over these infinite periods. And remember, the key here is to discount future values, because we're looking over periods in the future. To look at those values today, we need to discount them. So that's what we're also going to be doing. So let's just start by looking at consumption. So consumption over our infinite periods, remember, S is going to look at the future periods, and we're looking at infinite many periods. So consumption at time t plus S, and S again being 1, 2, 3, all the way up to infinity, is going to look something like this. So this is our consumption. It's over infinitely many periods, and we're discounting it by the interest rate, which is 1 plus R. This is an R. We're discounting it by the interest rate, and whatever period we're in, S, is also going to have an effect on the value of the discount rate, which again we're dividing consumption by, because we have to take the present value of consumption from the future. So consumption, the present value of consumption from our infinitely many periods is going to be equal to the interest rate multiplied by the asset that they're endowed with in the very first period. Because remember, as I was emphasizing, that they only get this asset in the very first period and they do not get it thereafter. So in the future, they earn interest on this asset, as in 1 plus R. This is the return they get on this asset that they were given in the very beginning. And that is, a form of revenue for future periods. That's what they're getting on top of, just holding the asset. They're going to get a return on it. And now for income that they are given in every single period, it's not going to be this case as it's not going to just be the interest rate multiplied by income, because we are given income in every single period. So we're going to have to do what we did with consumption, is sum it over our infinitely many periods. So from S equals 0 all the way up to infinity of income in the future, and again discounted by the interest rate and the state, or the period that we're in, will also have a say in our discount factor. And this is our budget constraint. It's very similar to the 2-period model. If you watch that video, it's very similar to that model, except because we're looking over infinitely many periods, we have to sum our values that we get in every single period, so income and consumption, and we have to discount them by the interest rate, and also depending on the exact period that we're in, which S is going to tell us that. So that's all that we're doing now in a model with infinitely many periods. So now that we have the budget constraint and we have the function that our consumers want to maximize, we now just need to solve the simple constraint optimization problem. So we have a budget constraint, and we have the function that we want to maximize that is subject to our budget constraint. So in this case, as I just said, this will be a constraint optimization problem. The way we're going to approach this specific problem and solve it is using Lagrangian. rather than just taking the slope of the budget constraint and set it equal to the slope of the indifference curve that is, as a result of the function that we want to maximize in utility, we're going to use Lagrangian because when things get a little more complicated, like in this case we have the interest rate that we're discounting by, we have summations, using a Lagrangian is a lot more, it's a lot easier. And a Lagrangian as a way to solve constraint optimization problems becomes a lot more of a useful tool when the problem becomes a lot more complicated. There's a lot more variables that we have to look out for. So I'm just going to write out the Lagrangian that we're going to optimize. So this is our function that we want to optimize here. We want to maximize, is our utility function that we looked at earlier of consumption discounted by b to the discount factor. Now our Lagrangian will have lambda in it. If you're not too sure what Lagrangian is, I won't have the time in this video to go over using a Lagrangian to solve constraint optimization problems, but a quick video or a Google search will kind of get you up to scratch on what exactly I'm doing here. But what we'll use is our constraint, insert our constraint right here, which, if you recall, looked something like this. Income discounted by rate of return. And this is our Lagrangian. This is what we want to, here's the function that we want to maximize, and here is the constraint that this function is kind of, the budget constraint limits us. So we can't just obviously consume infinite amounts of consumption. We're limited by our budget constraint. So here's the constraint, here's the function we want to maximize, and this whole equation is our Lagrangian that we're going to use to maximize this function. So to maximize this Lagrangian, the first thing that we have to do is take the first order conditions of the variable that we're kind of looking at. So in this case, just put that S there, we're going to take the first order conditions of consumption in the first two periods. So that would be period t, where S is equal to 0, and period t plus 1, where S is equal to 1. Remember, this is S. That is all we will kind of need to do in order to get from this equation that we're at right now, this Lagrangian, to the Euler equation, is take those first order conditions for those two variables, and from that we'll arrive at our Euler equation. So Ct, so in other words, Ct means when S equals 0. So in this case, we're not looking at, Ct is the period today, we're not looking at the future. So that would mean this summation would go away, this discount factor would go away, this would become Ct, not Ct plus S, and this would also become 1. So the first order condition of that from this equation, it would be quite simple. We would just end up literally, so we'll just say first order condition of Ct. That's going to equal, remember Ct enters this function, so it's just the first order condition of that function is just going to be this. When we're looking at Ct, there'll be no S, there'll be no discount factor, because remember S is going to be equal to 0 in the current period case. And our constraint, Ct enters the constraint here. Remember, S will equal 0, so the summation will go away, the discount factor will go away. So we're going to have lambda multiplied by Ct, and then when you take the first order condition of that with respect to Ct, you're just going to get minus lambda. We set that equal to 0 because we're maximizing the function, and that's what our first order condition with regards to Ct is going to look like. So now the first order condition for Ct plus 1, so now we're looking at a period in the future, which means our discount factor is going to be there, our summation and our rate of return, which discounts consumption in the future, is also going to be there. So it's not going to look like this case here. It's going to look a little bit different. And this is what we're going to do. Very similar to the first case, except now we're going to have the discount factor. Remember, S is going to be equal to 1 because we're looking at CT plus 1. The first ever period that's in the future, so it's going to be beta multiplied by the first order condition of the equation in t plus 1 multiplied by, so S is going to equal 1, so this is going to be CT plus 1 multiplied by lambda over 1 plus R. So when we take the first order condition of that with regards to lambda, we're just going to get this here. Set that equal to 0 because we're maximizing. That should be lambda, a bit messy there. So that's what the first order condition of this equation here with regards to CT plus 1 is going to look like. We've now, because we're looking at the future period, we've now got the discount factor here and here. So now that we've looked at the function that our consumers are going to maximize, the utility function, with respect to consumption, and we've looked at the budget constraint, which limits how much consumption our consumers can consume, and now we've combined those two into the Lagrangian, which is the optimization problem subject to the budget constraints. Now we've taken the first order conditions with respect to consumption, and we end up here. Now, this is kind of, we can get, just from rearranging these two equations, we will then get to our Euler equation, which is the optimum condition for consumption. All we have to do at this point now is some simple algebra to get there. We can see that lambda, we just take the lambda over there, then lambda will be equal to this. And we also see lambda here too. So we can rearrange this equation to solve for lambda and then set these two equal to each other. And then we can kind of get the optimal path of consumption over the two periods, period t and period t plus 1. So if we were to rearrange for lambda in this case, we would get this, t plus 1. And now, because we've got lambda equal to this here and lambda equal to this here, we can set these two equal to each other, and we end up with our Euler equation, which is as follows. And once more, we got here from combining the constraint and the function that our consumers want to maximize, put them together into the Lagrangian, which is our constraint optimization problem. So we want to optimize for utility of consumption subject to the budget constraint. We maximize that function by differentiating, and now we end up here at our Euler equation, which looks as this, the following way. That is consumption. It gets a bit confusing with the brackets looking similar to the C, but that's consumption at time t. This is consumption at time t plus 1 multiplied by beta, the discount factor, and the rate of return. So this is our Euler equation, which we got from maximizing the consumer's utility function subject to their budget constraint. And we did this using the Lagrangian. So using the Lagrangian, we derived our Euler equation by taking the first order conditions of consumption, and here we are. Now, the way to interpret this and what we can kind of take from our Euler equation, I have gone over this before in a previous video, but I'll emphasize it one more time, is that it tells us important aspects about the consumer and how they're going to behave. So more specifically, what it tells us is that the consumers are indifferent between this and this because they're equal to each other. So they're indifferent between these two sides of the equation. So they're indifferent between consuming a single unit of consumption, CT, that gives them marginal utility, so this, U of CT, they're indifferent between that and saving in order to consume 1 plus R units of consumption in time t plus 1. So the 1 plus R means, that's where the 1 plus R units of consumption is going to come from. And in the second period, so time t plus 1, they're indifferent between that, this here, and utility of consumption, marginal utility of consumption in time t.